Hi, everyone. I'm Meredith Kopinski. Thank you so much for attending this special colloquium. And thank you so much, Professor Rubin, for coming here to Tucson to visit us.
It's a fun drive
It is a fun drive. There's lots to see in Yuma.
through the Old West.
Noah Rubin is now an assistant professor just as of last year at the University of California, San Diego. And previously, he was a research associate, a postdoctoral researcher, as well as a PhD student in applied physics at Harvard in Federico Capasso's group. He did his undergraduate studies in physics at the University of Pennsylvania in 2015 and works in the field of polarization optics and nanophotonics. It's a great pleasure to have you here, Noah. I remember the first time you visited campus with Paul to measure I think one of your first Metasurface
Yeah, that's
optics in our lab. What year was that?
2019.
In 2019. And at the time you were still a graduate student. And what a very fine impression you made on me.
Thank you.
Because you were so interested in all of the students in the lab,
Yeah.
right? And we all went out to lunch and you just wanted to know everyone's life story, future career aspirations, interest in optics. And I've always had the opinion that the very best among us intellectually are also so deeply also curious about each other.
Thank you.
I know there's a lot to learn from each other. So with that, welcome and thank you for being here to give this colloquium.
That's very kind of you to say. Thank you, Meredith. It's a pleasure to be here. I'm happy to see all these fresh faces. I see many graduate students out there. As Meredith said, I'm a new professor at the University of California, San Diego. Before that, I was a researcher and eventually also a PhD student back at Harvard on the East Coast. So I'm new to this side of the country. This is my second time, though, at the Optical Sciences Center here in Arizona. The first time being in 2019, as Meredith said, when I came out here to meet Professor Chipman. And I feel like I've had many interactions with your college over the years at a distance. Even before I met them, I had studied many works of both Russell and also Professor Mansurapur. So to be able to meet them back then was a real watershed event for me, because previously I had only read their papers. In the case of Russell, somehow mysteriously, a bound copy of his lecture notes was somehow in one of the libraries at Harvard, and I would study it. And later I had the chance to bring Russell there, and he was mystified at how that ended up there and who contributed it. But I was learning from it before I even met him. Actually, Professor Mansurapur, I had the opportunity of meeting when I was an undergraduate. This must have been in 2013 or 2014 at the University of Pennsylvania. And he came and gave this extremely interesting talk at a group meeting for the lab that I was in about relativistic electrodynamics. And I just thought that was so cool. And in some sense, he stayed in my life over the years. I ended up being a PhD colleague of his son's. And now I continue to interact with him, which is great. So what I'm going to talk about today is a body of work that I've been working on since I was a PhD student. At first from a more device-oriented and fundamental perspective, and that's where we're going to start today, but through an area that I think is coming to practical fruition, in my opinion. So this is going to be a talk that spans all the way from the fundamentals of optics, at least at a high level, all the way to practical applications that I believe are coming to fruition and are being realized, both for science and also perhaps also in the consumer space, perhaps. So the instructions I was given for this talk explicitly, and I'm quoting the instructions I was emailed, is that this is supposed to be a Scientific American type of talk. And that's what I've aspired to do here today. So this is going to be very high level. Many things will be omitted. There are countless details that are not contained here. So I would encourage anyone to stop me at any point during the presentation or after to ask any clarifying questions. I'm an open book here. So this talk, I'm first going to provide a bit of introduction and motivation to this subject and why I think it's interesting. Then I'm going to introduce some theoretical underpinnings of this subject that I think are useful for understanding it mathematically and for designing this novel class of optical components that I'm going to tell you about. Then I'm going to tell you from that very general theoretical perspective how we can make a new class of devices, which I think are very interesting optical components for the problem of designing compact and simple polarimeters and conducting polarization imaging. And then depending on how much time I have left, I may talk about some more far out there applications in areas that I call Jones matrix holography and a recent work that we did on snapshot full Mueller matrix imaging polarimetry. So this being starting at a Scientific American level, we have to begin with polarization. Polarization, of course, is one of the things that makes light special in the domain of waves, in that light is a transverse oscillation. And from Maxwell's equations, we have this plane wave solution, which admits a description known as the Jones vector, which is a two vector that describes the trajectory of the electric field and can be parameterized essentially by two angles, which give its ellipticity and its angular orientation. That should be no surprise to anyone here. And what we learn even in high school is that that means that the polarization of light can be linear, circular, elliptical in the most general circumstance. The more general description, which I don't need to say for this audience, but I often do say when I'm speaking to more of a general physics audience, is that that's not the most complete description of the polarization of a plane wave, because it doesn't permit the fact that the light can be partially polarized, which is the basis of the Stokes formalism, which rather than a description of exactly what the electric field is doing, is an incoherent description that is specified in power units and it contains 4 parameters rather than 3, which is what the Jones vector would require. And it allows light to be partially or unpolarized. And that's what lends itself to this description known as the Poincare sphere, where we can depict different polarization states on the equator or at the poles for circular polarization, or in general in between for elliptical polarization. The other thing that bears repeating for anyone in this audience who may not know is that along with each of these descriptions of the polarization of a plane wave, either the Jones vector, which is a description of the electric field, or the Stokes vector, or the Stokes parameters, which is a description, an incoherent description of what the polarization state is doing, there are linear transformations that are given by matrix quantities that describe what optical elements do to the polarization of a plane wave. The simplest among these is the Jones vector, which is a 2x2 matrix of complex numbers that can specify what an optical element is doing to the polarization of a plane wave. That has 8 free parameters because we have 4 complex numbers. And then we have a Mueller matrix, which is a 4x4 quantity, where each of the elements is purely real because we're dealing with power units, and thereby there are 16 numbers. This is, again, the more general description of polarization optical components. The other theoretical underpinning that I believe underlies the work that I've done and that is necessary to understand what I'm about to talk about next is the concept of optical holography, which was the subject of a Nobel Prize in physics a long time ago, but in its original conception after the development of the laser was a way of recording wave interference and later reconstructing it. This is what Gabor originally conceived of. But an area that perhaps you're less familiar with, which I think really underpins a lot of what's being done today, is a field known as computer-generated holography. This is something that came out of the 1960s, also after the development of the laser. But in contrast to the type of holography that people like Gabor developed, where we were merely capturing the interference pattern of light scattered off of a particular object, in computer-generated holography, we could synthesize waveforms from objects that never necessarily existed in the first place, but that were simply described by computer. The term comes from the 1960s, when computer was a bit of a buzzword, when they were less common than they are today, of course. But the first computer-generated holograms were simply a realization that with engineered optical structures, we could create patterns that would shape waveforms in new and possibly arbitrary ways. And originally, in the 1960s, in these famous original papers from back then, this was realized by printing, essentially, with early computer printers. And in this way, people could synthesize holographic interference patterns by controlling the amplitude and phase of a wavefront in a very crude manner that was available to people at that time. So when we hear the word metasurface today, this has become a bit of a buzzword in optics. And I think I put it in quotes because I'm actually not myself a fan of the word metasurface. I didn't coin it. And we should clarify what's meant by that. Because in the optics literature today, metasurface has become one of the most common terms. However, its meaning is actually imprecise. People will describe any sort of engineered optical photonic structure as a metasurface, especially in particular if it's operating in free space. we'll see all sorts of structures described as a metasurface, using all sorts of materials at all sorts of different wavelengths, even in microwaves, when the features that are involved are macroscopic and can be seen by the naked eye. But one thing that I think is important to note is that what we call metasurfaces today are inheritors of work that's been done, at least since the 1960s, in the area of holography and computer-generated holography. It's just that today, with the advent of modern semiconductor fabrication techniques, our ability to print very small structures has become very, very advanced, to the point where we can very easily make structures, even in academic facilities, that are smaller than the wavelength of light involved. And I believe that that's the definition of a metasurface. It is a diffractive or holographic optical component where the constituent features, which primarily intend to shift the phase of a wavefront, are smaller than the wavelength of the light involved, and are separated with a pitch that's smaller than the wavelength of the light involved, such that any diffraction that occurs from these structures is purely zero order. That is, it's diffracting from ensembles of these structures rather than from the pitch between the structures themselves. That, I believe, is the definition of what a metasurface is, or at least it's my definition. So the point I wish to make is that this field, metasurfaces, is a modern incarnation of things that have been going on for a very long time in micro and nano fabrication, in the fields of metamaterials and diffractive optics and holography. But what I have continually asked myself throughout my, albeit somewhat short scientific career so far, is what can we actually do with these metasurfaces, these advanced diffractive optical components, that's unique for optical systems, that adds an advantage to optical systems that we didn't have before. And I really believe that the answer to that lies in the field of polarization optics. There are things that can be done with metasurface elements that cannot be done with a single component otherwise. I'm quite confident in that statement. Of course, there's some nuance to that. However, the reason for that comes from the very basic physics of birefringence. As we know, a type of optical components that we use to control the polarization of wavefronts in free space rely on a property of crystalline materials known as birefringence. This is the basis of all wave plates. This is the basis of polarization beam splitters. And it comes from inherent, inbuilt quantum mechanical properties, ultimately, of crystalline materials. Of course, we can make synthetic crystals, but by and large, we're relying on the properties of naturally occurring materials. And more than that, when we deal with a naturally birefringent material, the axes of the birefringence and the thickness of the material, everything about the birefringent transformation that might be applied to a wavefront is constant over the clear aperture of the crystal. There's no or very limited possibility to engineer on a small scale what that polarization transformation is. On the other hand, there's another type of birefringence in physics, what we might call form birefringence. And that comes from the anisotropy in the shape of something that is structured at or near the wavelength scale of light itself. We're familiar with that for anyone who's ever used a waveguide or an optical fiber, for instance. If we have a waveguide, for instance, a dielectric waveguide, if it's structured in a way that's anisotropic at or near the wavelength scale, we'll have different modes. And the modal index difference between those modes can be engineered by changing the aspect ratio of this structure and its shape and size. And so that hints that if we have the ability to control the shape of things, then we can create birefringent properties that we otherwise might not be able to access with natural materials, or engineer things spatially in a way that otherwise wouldn't be possible. And that's really what makes these metasurfaces special in the domain of polarization optics. It's that at each point on, indeed, a subwavelength lattice, we can place a different structure that light sees as anisotropic. So for instance, if we have light transiting through this structure, which I'm just showing here as a little cartoon, at each point, the wavefront could encounter a structure which is anisotropic in a way that can be controlled by the designer, because these structures are fabricated lithographically. We have complete freedom to control the transverse cross-section of these structures. And so then at each point, an optical wavefront could encounter a structure where we're able to engineer the overall phase shift that the light experiences, the retardance that the light experiences, and the fast axis of the retardance that the light is experiencing. This is a possibility that is simply not possible with traditional birefringent materials. There have been other, to be clear, there have been other types of optical elements in which people have researched this type of spatially varying polarization control, most notably among them liquid crystals. However, it's my contention that these metasurfaces offer a higher degree of spatially varying polarization control than almost any other technology that has yet emerged. Maybe Russell will argue with me about that. In particular, what we can think of is that at each point on this subwavelength lattice, light is experiencing a different Jones matrix, where at each point, by adjusting the dimensions of a structure, in this case, I've just drawn it as a rectangle, but it really could be almost any transverse shape, light will experience a wave plate with different phases imparted on the polarization states that are along these symmetry axes, and that can, in general, be rotated at an arbitrary angle. So we have these 3 degrees of freedom at each point. Now, there's a different question, which is that if you accept that we have that degree of freedom, we have this way of engineering the polarization transfer function that a wavefront experiences. What do we do with that? How do we understand how light behaves when it encounters one of these obstacles, and how do we design these to achieve some desired function? This is the domain of Fourier optics, and in particular, a slight generalization of Fourier optics that we term Jones matrix Fourier optics. So before we talk about this Jones matrix Fourier optics, we should just talk about normal Fourier optics. I can summarize much of Fourier optics in the following statement. If we have some electric field at some plane in space, which I call u of xy, which is just the amplitude of the field, if we take its Fourier transform, we operate in the plane wave decomposition of that field, and the propagation forward in space of each plane wave is mathematically trivial, so we can apply the correct phasor to each of those plane waves and then reconstitute it with an inverse Fourier transform. I think that statement encapsulates much of what the subject of Fourier optics is. On the other hand, what if we have light, for instance, a normally incident plane wave, encountering an obstacle, such as a metasurface, but not necessarily a metasurface, that exhibits a spatially varying polarization transfer function, as encapsulated by a spatially varying Jones matrix transformation, which would be 4 complex functions as a function of space that are assembled into this spatially varying Jones matrix. How do we understand how light will then subsequently propagate? Well, what we can think about is that when light hits this, it will depend on the polarization state of the light hitting it, what will come out. But there's a way of treating this that's completely agnostic to what the incident polarization state is. And that's what I term Jones matrix Fourier optics. What we can do is we can actually take the Fourier transform element-wise of this spatially varying Jones matrix function that describes the optical component itself. And what that will give us is a second Jones matrix function, which is now in spatial frequency space, in the angular spectrum Jones matrix, which will give the polarization behavior of all of the plane waves in the plane wave decomposition that light will experience after going through this optical element as a function of what the incident polarization state was. Now, this actually has quite some antecedents before our work in many domains, including in Professor Chipman's work, where this was used in sort of the opposite sense to characterize polarization aberrations of existing optical systems. And I think in your work, you call this the amplitude response matrix, if I'm not mistaken. However, in this case, what I'm going to show you here is that rather than characterizing existing polarization effects of optical systems that happen to be there, we can very explicitly engineer them. The point being that if we have an optical element such as a metasurface, which exhibits a spatially varying Jones matrix, when light hits it with some incident polarization state, which I draw with this ket here, J in, the point is that this matrix A, which is the element-wise Fourier transform of this spatially varying Jones matrix, which describes the optical element itself, will give the polarization transfer function of every plane wave that exits it. And it will give it as a function of what that incident polarization state is. So this, to me, gives the most succinct way of viewing the power of these optical elements in the broader context of polarization optics. The way to view one of these metasurface polarization optics is a parallel polarization device where every part of the far field, in terms of its angular spectrum, could potentially implement a different polarization optical element. And these all could be encoded in one holographic optical element, that being the metasurface. To be a bit more explicit, let's say, as a designer, this is still a bit abstract, you say that you want this optical element to implement all of these different polarization effects in the far field as a function of angle. Well, then all you'd have to do as a designer is take the inverse Fourier transform of that. That would give you the spatially varying Jones matrix that this metasurface optical component would have to implement. And then you'd have to simply compare that to some physical implementation that you want to make that out of, such as the dielectric structures that I was talking about some slides ago. So that's a very high-level view of why these metasurfaces are special in the context of polarization optics, what they can do at a very high theoretical level. They can multiplex many different polarization optical elements into one component. But maybe what you're wondering now is, why does that matter and what practically can we do with that? So I will go over several applications that we've been working on in previous years in that direction to try to make some use of this. So the first application here, and the one that we've gotten the most mileage out of, and that of which Russell and Meredith are well aware, are what we call polarization analyzing gratings. And what I mean by that is a special type of diffraction grating that when light will hit it, it will split into a finite set of diffraction orders, where each of those diffraction orders will act akin to a polarizer. It will act as an analyzer for a different polarization state. In some ways, you can think of this type of device as a generalization of the polarization beam splitter. Whereas a polarization beam splitter, light comes into it and it has two channels of polarization analysis, which are moreover constrained to be orthogonal. In these types of devices, when light will come in, it can be directed to an arbitrary number of channels where the analysis states for these polarization channels can be arbitrarily specified by the designer. Well, almost arbitrarily specified by the designer. And the number of channels can in general be greater than 2. So how this works in the context of the Jones matrix theory I told you about before is, let's say you're going to constrain this Jones matrix function to be periodic, which means it can be described by a Fourier series. You select some diffraction orders, let's say it's some set of diffraction orders. You say what you want these diffraction orders Jones matrix transformations to be. For instance, polarizer-like Jones matrices for a specified set of polarization states. And then directly by Fourier series, you can synthesize what the required Jones matrix is. The way we design them is actually a little bit more sophisticated than that, but that gives you the gist of it. And then you can implement one of these that when light will hit it, it will split into a finite number of channels, each of which has its own Jones matrix and could behave potentially in a polarizer-like fashion. Skipping a lot of detail, I want to show you an example of one of these devices. So this is one of the first such devices we made. And what you're looking at here is just a picture of a unit cell that we repeat hundreds to thousands of times to make a bulk diffraction grating. What you're looking at here in this particular example are structures that are made of titanium dioxide, which is a high index dielectric in the visible regime. That's important that these are high index actually for the way that they work, high refractive index. And we tile this to make a bulk diffraction grating that when light hits it in a way that you have a laser beam incident from behind this screen, it will split into a finite number of diffraction orders. And I've shown these in K-space here. This grating is designed such that the energy will primarily concentrate in the inner diffraction orders of this two-dimensional grating in such a way that each of these diffraction orders act like a polarizer for the 4 polarization states that I've drawn here. Well, you might ask yourself, why these seemingly random polarization ellipses? This set actually corresponds to a set of 4 polarization states that if you were to choose any 4 polarization states, these are on average as different from each other as any 4 polarization states could be. Another mathematical way of saying that is that in the Poincare sphere, the locations of these polarization states trace out a tetrahedron, which optimizes the sphere packing problem for 4 points, which is a way of saying these are as different from each other as they can be, which means that this actually can be a very interesting and useful element for measuring the polarization of light. In other words, well, before I get there, if after this diffraction grating, light will hit it, if on each of these 4 diffraction orders we put a photodiode, the information measured from those photodiodes in a snapshot from a single component is actually sufficient to constrain what the full Stokes vector of the polarization state is. And if you were to choose any 4 polarization states along which to analyze the light, you would like to choose, for instance, these 4, which can be shown to maximize the signal-to-noise ratio of that measurement because they're maximally different from each other. Now, that would be sufficient, for instance, for measuring the polarization state of a laser beam. But what's really interesting are systems in which you can measure the polarization state of light across a photographic scene for a remote sensing type of application, as many people here work on. In that case, if you take one of these gratings and you place it into the pupil plane of an optical imaging system, which here, just for simplicity, I'm showing as a single lens, which is almost sacrilege when I do that at the University of Arizona, so I hope you'll forgive me. What will happen schematically is that light will divide into these diffraction orders where we're concentrating the energy in a way that depends on the incident polarization state. And if we do things right, including a color filter to keep things relatively monochromatic, and a field stop to prevent different images from overlapping on the camera sensor, we can have multiple images of a given scene that when we recombine them pixel-wise, that's sufficient information at each pixel of the scene once we've registered the images to each other, which is actually quite a subtle process, as Russell always likes to remind me. And we can constrain what the polarization state is at each pixel. So in our initial work, this is already quite some time ago, when I was a graduate student, I built this box around one of our gratings with a singlet lens just to show that we could make an extremely simple, extremely compact polarization camera that could potentially be mass producible, that could get the full Stokes vector in a simultaneous acquisition from a single image. Yes?
How can you tell the difference between lower degree of polarization and efficiency for the surface?
Well, you have to calibrate it ahead of time. So combined with the calibration, it's possible to disambiguate those effects. Yeah. Did that answer your question?
Mm-hmm.
Okay. Yeah. So to give you an example, these are some real photographs that I took when I was a graduate student in the parking lot outside my lab. And we have a system where we have these 4 images. And each of these, although you can't tell it from this image, have been analyzed with respect to a different polarization state, although there are no actual polarizers in this system. It's actually just this grating is the sole polarization optical component of this system. Now, to implement this without this grating would require an assembly of at least 4 beam splitters that are all cemented together and would, in general, necessitate 4 different image sensors. So in our initial work, we showed a number of examples of real-world polarization effects that you could see with this. These are the sort of real-world polarization effects that people here study and are familiar with. In each of these examples, the first row shows like the raw image that would be seen on the camera sensor behind one of our gratings. Then we can process it through the calibration, and you can portray what what a monochrome non-polarization camera would see. What the angle of linear polarization is, that's what I call it the azimuth, that's the orientation of the polarization ellipse, and the degree of polarization. I won't go through all these examples, but the first one is actually sort of an artificial one. It's just a wheel of film polarizers that I cut in the lab. I did some arts and crafts. Of course, if you just look at what a monochrome camera would see, you can't really even tell these are polarizers, but with the polarization information, you can see that they're oriented radially outwards and that the light passing through them has a high degree of polarization because it's a polarizer. You can even see that in these raw images, that in each of the sub-images, different parts of the wheel are dark and bright because you have different polarization analyzers. Some more interesting examples, one that I know is close to Meredith's heart, is that this example is a soda bottle. You might not have known that if I didn't tell you. It's a specularly illuminated bottle of Canada Dry, and we're looking down the top of it, and you know, it's a soda bottle, so it's going conically outward from you. And each of the rays that are coming into the camera have specularly reflected off of the surface, but we know that the surface is rotating around. So from a normal monochrome photograph, you have no indication of the 3D nature of this object, but from an angle of linear polarization image, you can see it sort of pinwheels around from all the way, you know, all the way around, and that gives you some priors on what's known as shape from polarization. Meredith is a real expert in that. You can do the same with my colleague Paul's face, which suggests perhaps some biometric application. And there are polarization signatures from outdoor objects, which should be familiar to anyone who's put on a pair of polarizing sunglasses. Back in the day, we even made custom software to do all of this in real time. You can see this is my colleague turning that wheel of polarizers, because this acquisition and data processing is happening instantaneously because it's from a single frame. Well, not instantaneously, but you know, in the sub-second time scale. This one was one of my favorites. I always like to joke that this video looks like it was taken in 19th century Paris. It wasn't, but yeah, it looks like a daguerreotype. But it's just because the computer was running a little bit slowly that the frame rate is low. But you can see there's a corner at the end of this street, and I like to point out that as the car rounds the corner, this image, which shows the angle of linear polarization, as the car changes, the color changes because the surface normal of the vehicle actually oriented in a different direction, which is expected. So I just want to say that in the broader context of architectures for polarization imaging, and we have some experts on this in this room, I feel that these type of gratings in certain domains can hold some advantages because the normal type of architectures would be what's known as division of time, which would mean you either have a switching liquid crystal panel or more commonly a rotating wave plate in front of your camera. And you have to take multiple exposures as the thing turns, which is obviously very undesirable in many applications. Or if you wanted to have a simultaneous polarization state measurement, you would have to have a sequence of beam splitters and different polarization optics that would have to analyze this, and generally that would entail multiple camera sensors. A more modern option is division of focal plane, which means that people pattern polarizers above camera pixels in the same way that color imaging is done, except they do it with polarization filters. This too has some disadvantages in that the fabrication can be quite difficult, and it uses absorptive polarization filters. In years since that initial demonstration, we've done a lot of things, which I'm only going to talk about very briefly. One was that we showed that in addition to making a dedicated polarization imager around one of these gratings, you also could design these polarization gratings in the correct way, that they could be a screw-on attachment to an existing camera in a way that converts it into a polarization-sensitive camera. So if I just, in this work, we took just a normal machine vision camera and screwed something on the front that had one of these gratings in it, which with a single component converts it into a polarization camera where it wasn't one before. In the context of a NASA project, when I was a postdoc, we did quite some work on trying to figure out how accurately we would be able to measure the polarization state of light using one of these gratings, and actually inspired by some of Professor Chipman's work from 2010 on ways of detecting how accurately the degree of polarization can be measured. We showed that it could be done at the 10 to the minus 3 level through one of these gratings, which was very important for some NASA problems we were working on at that time. Something else I want to say is my PhD advisor's startup company is attempting to commercialize this for biometric authentication applications. It was in Wired magazine. I read an internet rumor the other day, and of course it's just an internet rumor. I'm totally out of the loop. That it may be in the next generation Samsung Galaxy, but I don't know. We can hope for that. Something we did more recently is that we wanted to be more ambitious. With these gratings, we were able to miniaturize the polarimetry parts of these imaging systems. However, they in general still require a camera lens. If we're doing that over a wide field of view, the camera lens really is what dominates the size. So we were ambitious. We wanted to also make the imaging part of this integrated, and we patterned on a piece of glass on one side one of these polarization gratings, something that looks like this, and on the back side we patterned essentially a diffractive optic lens. And what will happen is that incident light, these are not different colors. The colors here are actually just different ray angles, not different wavelengths. Light will hit it. It will go into one, I'm just depicting one diffraction order here. When it hits the back of the substrate, it will image in a way that if you design it correctly, not shown here, it can be quite telecentric, and it will form an image, something like this. This is imaging at 870 nanometers over a relatively wide field of view, 40 degrees. Maybe that's not a wide field of view here, but it was for me. All this optical system is it's a camera sensor, a color filter, and a box which acts as a field stop. It's an extremely simple optical system, and we're able to get images like this in broad daylight. I show a picture of a car because the car was actually moving. I showed the image of the car to show that even this very tiny micro optical system with a 1 millimeter entrance pupil can acquire images in tens of milliseconds, enough that the car isn't blurred while it's moving. This is another picture outside my old lab. This was in the near infrared, so the leaves appear white. But again, each of these images here are polarization analyzed in a way that when we combine them, like of this Prius, we can say what the different polarization parameters of the scene are. We also characterize this camera for being so simple and having no actual lenses can actually have a qualitatively impressive resolution. Like I could read that 20-mile-per-hour speed limit sign on the street from one of these images. We also characterize its MTF. That was in the paper. Another project we've done with this recently, which I'm quite excited about, is in the area of solar astrophysics, also with NASA support. And whereas everything I've talked about in previous slides was mostly in my academic past as a postdoc and PhD student, this project is something that has only recently come to fruition at UCSD. Solar physics is, of course, of fundamental interest. There's great scientific interest in understanding the dynamics of the sun, and it's still really a mystery of science about how most things work with the dynamics of the sun. But it's also worth pointing out that there's significant economic interest in understanding the sun because coronal mass ejections, if severe enough, could really ruin a lot of our electronics, both on Earth and in low Earth orbit. So there's tremendous interest in being able to better understand and model the sun. The magnetism of the sun seems to have a very important role in how it works. And as many people in this room may know, polarimetry is actually one of the primary means by which that magnetism is remotely characterized because the magnetic fields on the sun produce polarized light primarily through the Zeeman effect, but also through more obscure quantum mechanical effects such as the Hanle effect. And from these effects, we can observe remotely the magnetism that's on the sun. However, if you look at the instrumentation that's used to characterize the magnetism on the sun through polarization state measurements, it can be very, very complicated. And I don't mean to oversimplify this. There are very good reasons why the instrumentation is very complicated. However, let's just focus on the polarization analysis part of this. I've shown one instrument here on the left, which is a ground-based instrument in Europe, and one instrument on the right here, which is a solar telescope that's in low Earth orbit for doing these sorts of measurements of solar magnetic fields. In the one case, we have a ferroelectric liquid crystal polarization modulator, which is a high voltage active component. On the ground, maybe that's fine in an observatory. On the right, in the space-based polarimeter, you'll notice we have 3 or 4 instruments that all share a common optical path behind a telescope, and they all, along the optical path, share a rotating half wave plate. If that mechanism were to fail, the entire instrument would be done. There would be no more polarimetry. And in fact, my solar physics collaborators have made me aware that that's actually happened. There have been sounding rocket missions where the entire thing was essentially ruined because the stage broke. Something beyond the active components, something that my industrial partners made me aware of is that actually the fact that you have to take measurements of the sun as a wave plate rotates is highly non-ideal for a space-based application. Because the very fact that the images are being taken at different times is very non-ideal, because I'm not a mechanical engineer, but what they've told me is that these space platforms are continuously jittering. And they undertake great mechanical efforts in order to stabilize the pointing of these satellite buses. And often, it's the non-simultaneity of the polarimeter that's driving some of the strictest requirements in these space missions with regards to pointing. So if there were a way, a simple hardware solution to do this measurement simultaneously with a minimum of componentry passively, that would be a really big deal. That's what motivated us to do this project in collaboration with what was Ball Aerospace, now BAE Systems, I should change the logo, and the National Center for Atmospheric Research. In collaboration with them, we designed a simple refractive telescope that is in most regards ordinary, except for the fact that it has a pupil plane near the end, which is sized to place one of our special polarization analyzing gratings. And then on the back end, form 4 images of the sun at an absorption feature on the sun that we selected around 460 nanometers. As a part of this, we undertook a very intensive effort to make the highest performing version of one of these gratings that we've ever made, which had a 6mm clear aperture, which when we talk about free space optics, that doesn't sound very large. But it's very large for one of these elements that's being made by electron beam lithography with features that are hundreds of nanometers in size. And we were able to perfect the fab to such a degree that the efficiency of this optical element at the design wavelength in terms of the amount of energy directed to these first orders was around 70%, which is impressive when you consider that if you actually used a polarizer in your optical system, the efficiency would be at most 50%. So that's one advantage of these components too, because they sort light rather than filtering it, they can actually have a higher efficiency. And the polarization selectivity of these orders was quite high, 98 or 99%. Moreover, I'm not sure if I mentioned this, in collaboration with BAE or BAL, we space qualified these optical elements and raised them to a high technology readiness level as defined by NASA. Yeah. And last summer, we had the privilege of actually taking this telescope with the special component in it and integrating it with the former flagship solar telescope of the National Solar Observatory. Previously, for many decades, as Russell knows, this was the premier solar astronomy facility in the world. They've since all moved to Hawaii, where there's this Daniel K. Inouye solar telescope, which is really state-of-the-art. This one's left over for people like us who have research concepts that we just want to try out. And we took our telescope, we were able to pupil match it to the big telescope. And yeah, here's some more pictures. Here's our team at the observatory with light coming from the sun. And we use this in two different modes. In one mode, we integrated it behind a tunable Fabry-Pro etalon. And you would get raw images like this of the sun. This is the limb of the sun with a sunspot. This is near the disk center of the sun with a sunspot grouping. And what we do is we tune the Fabry-Pro etalon over these strontium and iron lines that we were looking at. And then comparing it to a calibration, we can say what the Stokes parameters are as a function of wavelength as we tune across these lines. And in the circular polarization, we see this sort of feature. Here are the spectral lines through the Fabry-Pro etalon. And we have this feature, which looks like the first derivative of the line, which is characteristic of the Zeeman effect. And from the magnitude of these sort of oscillations, you can comment on what the strength of the magnetic field is at each point within the sunspot. You can map the longitudinal magnetic field. Another architecture that we showed is that it's actually also possible to integrate this with a grating spectrometer. So there was a grating spectrometer on site. We can put the same instrument behind it, and then we get images like this, where in each sub-image here is still the polarization as mediated by one of these special gratings. Then along this direction is the spectrum. So these two lines are these two absorption features that we were looking at on the sun. And then this direction along the slit of the spectrograph is actually space along the sunspot. And then you can scan a slit in the spectrograph to form a full image of the sunspot. And likewise, then at each point within this sunspot, you can map the magnetic field. You can map the Stokes vector, from which it's actually possible to derive the longitudinal magnetic field, the field that points at you from the circular part of the polarization state, and the transverse magnetic field. You can actually see some evidence of that in this signature, which looks like the second derivative of the line, which, as predicted by quantum mechanics, would be related to the transverse magnetic field, which produces linearly polarized light. They call that sigma and pi when people describe the Zeeman effect. As a cherry on top, we actually were able to compare those observations with a NASA mission in orbit called HMI, which is continuously monitoring the sun every 10 minutes. And we showed, with some systematic errors, of course, for this initial demonstration, that actually what we were able to predict through our instrument acquired in a significantly simpler way. This NASA instrument uses a rotating wave plate that we got very similar magnetic field values. These values are in Gauss physical units to what was seen by the state-of-the-art instrument in orbit. So we're very excited about this, and actually with BAE, we hope to pursue a mission at some point in the future. Speaking of NASA-type applications, I wanted to have a shout out to this very early stage project that's being led here at the University of Arizona by Meredith, who's the PI, which we call the CHIRP, the Channeled Infrared Polarimeter. This is also a polarimeter for, in this case, atmospheric science in the long-wave infrared, which will include a metasurface component, which is playing a rather different role. In a sense, it's functioning where there are very few good polarization optics in the long-wave infrared, and we believe that we can acquire significant systematic advantages with one of these metasurface gratings in the long-wave infrared. How much time do I have? I could keep talking. It's scheduled until 5, but I feel like that's a long seminar. Okay, then I'll rush through this. So I've been talking a lot about polarimetry, and the polarimetry I was talking about was measurements of the Stokes vector. That is, measurements of the polarization state itself. There's another interest in polarimetry, which is that if I have an object, how do I measure the polarization state transformation that it enacts? That's known as Mueller matrix polarimetry. In other words, the distinction is between measuring the polarization state itself and measuring the transfer function of an object. Now, Mueller matrix polarimetry is substantially more complicated because the Stokes vector has these 4 parameters. The Mueller matrix has 16, so it requires 16 independent measurements. You're smiling. Maybe that's not fully correct because...
No, it's completely fully correct.
I
like the way it landed.
That's good.
Because 16 equals 16.
That's good. That's good. So there's some desire not only in measuring the Mueller matrix of an object, but also imaging what the Mueller matrix is over some spatial extent. To the best of our knowledge, and maybe I'll be corrected, there had been no system that could measure the full Mueller matrix over an image in a snapshot. In fact, there had been some proposals in the optics literature, which by and large were very, very complicated. They would require either many polarization gratings, many subart plates, which is kind of a complicated polarization optical element. We came up with a different scheme. Our scheme is an example of what's known as channeled polarimetry. It uses Fourier domain concepts that are well known in this community, actually. And the way we accomplished it is we realized that if you could generate a spatially varying polarization state illumination, then if you were to measure the polarization state that would come out at the output, then that was sufficient to constrain what the full Mueller matrix was over an imaging field of view. So this is a bit complicated, but if you engineer the incident polarization state to be something like this, in that over an image, it has some spatially varying Stokes vector, which is given by this, which just has some oscillations in each of the different Stokes components. Well, then in the Fourier domain, that's like upmodulating each of the different Stokes components to different spatial frequencies, you could say. Then, when this spatially varying polarization state interacts with an object that has a 4x4 Mueller matrix, where the Fourier domain, the spatial frequency information about each of those Mueller matrix components is depicted by each of these symbols. Well, then if we do the matrix multiplication, each of those Mueller matrix components gets upmodulated to a unique place in spatial frequency space, which then, as long as you're band limited, can later be cropped in the spatial frequency domain and essentially demodulated in a way that allows you to constrain independently and fully what all 16 elements of the Mueller matrix are from a single Stokes vector measurement. And then if we do this with metasurfaces, this can actually be accomplished with an extremely simple optical system that has only 2 polarization elements, those being 2 metasurfaces. One, on an input that when light will hit it, will prepare the correct spatially varying polarization illumination, which will then interact with the object. And then if we then image it with a single shot polarization camera enabled by one of these metasurfaces, it's sufficient to specify from a single shot what the full Mueller matrix was over the imaging field of view of this camera. Of course, with the penalty that because you're upmodulating things in the Fourier domain, you lose some resolution. Nothing comes for free. This is an example of what such a Mueller matrix imaging system would see for air, where there's nothing in between. And you can see that in each of these images, this is a different polarization channel, and we can see different spatially varying polarization patterns that are being measured here. And then if, for instance, let me see if the video plays. What we can do is we can place a polarizer into such a system, and as we rotate it from just that single image acquisition, we can specify how the polarizer, was oriented and what all the Mueller matrix elements are. I know we have some real Mueller matrix imaging aficionados here who are going to ask me about the errors in the crosstalk. I will emphasize that this was a very preliminary demonstration. in our work, we applied this to all sorts of different polarizers and wave plates, as well as an off-the-shelf vortex retarder, which has a substantially more complicated Mueller matrix image. Okay, how am I doing on time? I can have 5 more minutes because I think this is very cool. I don't know what it's good for, but I think it's very cool. Maybe quantum optics. That's what people say when they don't know, right? Just kidding. Yeah. So I started out the beginning of this talk talking at a very high level about this Jones matrix Fourier optics stuff, kind of rather theoretical. And then I immediately jumped to this scenario where I was just talking about these fancy diffraction gratings that can analyze polarization. And we've kind of stayed with that specific application since then. I want to back up for a second and go back to the most general application in which we, in general, unlike a diffraction grating, have an aperiodic optical element, which is described by this Jones matrix function. In that case, rather than splitting into discrete diffraction orders, the light will emerge into a continuum of plane waves. It will form a true holographic image. We can also engineer the polarization behavior of an entire holographic image, not just a small number of discrete diffraction orders. And we can say what the Jones matrix of each part of that holographic image is. This is the ultimate promise of what I was saying before of multiplexing many, many different polarization optics into a single optical element. And that's what I call Jones matrix holography. So let me just give you an example of something that we can do without being too specific about how it works. In this example, and this is real experimental data, we can design a metasurface using means that I can explain if you're curious, that forms a holographic image where I've designed each part of this holographic image to be a depiction of a different polarization state, a different polarization ellipse drawing. And because of the multiplexing ability of the metasurface that I described, I, as the designer, can actually say that each of these drawings is polarization sensitive to the polarization state that the drawing is of. That's sort of very deep. So if I had it here with me, and I don't have the sample anymore, but if I did, if I went like this on the table, by looking at the picture with your eye, you can actually figure out what the polarization state of the light illuminating it is. That's what you see in these pictures. In the lower left corner, I've drawn the polarization state of the light that was illuminating the sample. And then these are the pictures that you actually see on a screen with your eye. When it's this one, the X polarization is the brightest. The Y is dark because it's orthogonal. The circulars are half as bright. I can even take this further, and I can take the Poincare sphere, and I can make a hemispherical projection of it into the holographic image. And I can mix features like the longitude and latitude lines and the width that are not polarization sensitive with features that are polarization sensitive, which are the drawings of these polarization ellipses. So for instance, as I rotate a linear polarizer in front of this, you'll see that things get bright and dark as I rotate it, and you could actually ascertain by eye what's happening. And this is my favorite. When you rotate a quarter wave plate, as the light goes from being one circular polarization to another, the poles get bright and dark. Yeah. So maybe that's a good place to conclude. I think that's a fun conclusion. I want to say that I say it's a recent-ish review article. That was 4 years ago. But I put a lot of work into writing this review article some years ago that I think really summarizes the principles of this field, and from the theory to the applications, and in addition, a number of other technologies that are not metasurfaces that have also attempted to realize this type of spatially varying polarization control. I would encourage you to take a look at it. It's almost book length. And I would like to conclude by saying that I think these metasurface optics can enable new possibilities in polarization optics and instrumentation, which otherwise is a very old field. And it's exciting if we can bring some new hardware to it. I believe that it can allow the simplification of polarimeters. And I hope that this is reaching a level of maturity that it actually can offer benefit to real applications, for example, in solar physics, but also potentially many other areas. I want to say that I'm a relatively new professor. I'm just establishing my group at UCSD. I'm always looking for talented and motivated people. Going forward, the type of work I hope to do is a bit like what you've seen here, some of which did occur at UCSD, which is both on the application side for applications for instance, for NASA, but also in healthcare and other areas. But I also hoped to push new ideas in polarization optics into more fundamental areas, such as in ultrafast optics, nonlinear optics, laser physics. And I have some ideas in that direction. And I'm always looking for, especially a postdoc, especially someone who has a strong physics background. I think that would be really ideal, who's open-minded to think about new ideas in optics and in polarization optics in particular. So feel free to get in touch if you think you might be interested in that. We have some funding from NASA and NSF. I would like to acknowledge my many collaborators over the years, including my PhD advisor, and especially Dr. Lisa Lee, who was very important in much of the work you saw here and who was educated here at the College of Optical Sciences. And I would like to, of course, thank our many funding agencies, which include the Air Force and also NASA. And I think that's where that's my last slide. Yeah, so thank you.
Some questions?
How are you control? Oh.
I don't know. I think they like the recording. Let's let them first.
I saw that you didn't cover a lot about the design process of these gratings.
Complicated, but I'm happy to talk about it.
Just a brief summary, like if you use inverse design or like a library-based approach. And I also was just interested if that's something that you're researching right now, better ways, future ways to do it, developments in that.
Yes, all of those questions. Depends what one means by inverse design. Does it involve gradient descent optimization? Yes. Is that sufficient for it to count as inverse design? Yeah, it's this borrows from methods of diffraction grading design that have a lot of precedent that are here generalized to work with polarized light with some of the theoretical generalizations that I talked about in this talk. An important limitation of them, because they use Jones matrices, is that it really only works in the paraxial limit. But actually, as is the case in optics, they tend to work quite well even outside of that limit, even if they were designed under that assumption. So actually, when I was a graduate student, I wanted to better understand the paraxial limits of these designs. And I was pointed to a paper of Masood's from back in the day, where you had some dispute with Emil Wolf about the longitudinal component of the field in the plane wave decomposition. Yeah, that was fun to read back then. Yeah. Yes. Oh, I'm sorry. I'm so sorry.
So how much of an issue do you run into with parasitic orders degrading your image quality, and how do you control for parasitic orders?
That's a very good question. So there will always be parasitic orders, both in transmission and in reflection. It's inevitable. Now, the special thing about it being a grading is that there is an angular separation between the higher orders and the actual orders that you care to image. So long as those higher orders don't reflect off of some other element in the optical system and then the light ends up on the sensor anyway, you can generally avoid them. Now, there's a lot more nuance to that question, because also in gratings, in the highest performance gratings, people are concerned about light that ends up in between diffraction orders, which can come from low spatial frequency errors in the grating itself. So far, we haven't characterized that carefully, but it hasn't been a problem so far. I don't anticipate that it would necessarily be worse than in other types of diffraction gratings. Yeah.
You showed a slide earlier when you had a flat surface with arbitrary polarization state, and you said you need a 2x2 Jones matrix to Fourier transform and propagate the beam
Yes.
to the far field
Yes.
or near field. But if you just look at the two components of polarization, let's say X and Y on
Yes.
that flat surface,
Yes.
you only need two Fourier transform. One for each, one for X, one for Y polarization. Why four components?
That would be if you knew what the incident polarization was already. So we're specifying an operator language around these type of elements, right? So if I told you a priori that I was illuminating this object with some specific polarization state, then yes, it would generate a vector valued field, and two Fourier transforms would be sufficient to specify what happens. The point I was trying to make about the Jones matrix Fourier optics is that it's a way of describing the behavior of the optical element that's agnostic to what the polarization state coming in might be, which is a way of actually describing functionally what it's doing with the polarization of the light. And to fully specify that, you need 4 Fourier transforms. Does that make sense?
Yes.
Okay.
Thanks.
One more question?
Hi. So you, in the sort of microscope images, you showed that the structures are very small on these metasurface gratings. How stable are they to like mechanic? Like how impact resistant do you have issues where they tend to shatter or break or things like that?
Impact wouldn't be good. Also, physical contact isn't good. But vibrations and temperature, very, very resilient. As I said, we worked to space qualify this for launch. Yeah, I think, and there are strategies to make them even more resilient, particularly to other effects like high power laser irradiation. There are a lot of applications, none of which I talked about here today, but where you might want this to be able to handle very high peak powers. It's also possible to make these monolithic, like you make them out of just one material. That helps with that. There are ways of encapsulating them that could help with actually, for instance, if like other optics, you wanted to wipe an acetone wipe across them, then that might be possible with the right encapsulation. Physical contact wouldn't be good, but other stressors are okay. Yeah.
Thank you so much, Noah, for the
Thank you.
Colloquium. Let's thank our speaker one more time.